What's up, everybody? It's Miss Brothers. Hey, let's take some time and let's go through, this is Charles' Law, practice number 1. So we did Boyle's Law, and Boyle's Law specifically deals with the idea of pressure and volume, that indirect or inversely proportional relationship P1 V1 equals P2 V2. Charles' Law is a little bit different because that is specifically dealing with both temperature and volume, and so we're going to deal with that. And that formula is a little bit different as well, and we'll kind of go through that. Now, just know that I am going to be doing these problems using this little help tool that I created the other day, and specifically we're going to be in this second set of rows here and using that in order to help our way through these problems. But as you remember, the first part of these problems, there's some conceptual ideas, and then there's some work that we'll do with these problems. So let's get started. It says a balloon is filled with 3.0 liters of helium at 22 degrees Celsius, then placed outdoors on a hot summer day when the temperature is 31 degrees Celsius. And for those of you that aren't super familiar with the Celsius scale, that's usually about 90 degrees Fahrenheit. 30 degrees Celsius is a hot day. Now, remember, you guys, if we are dealing with Charles's Law, we are dealing with the pressure remaining constant when our variables of volume and temperature are changing. So the first question is this question, question A, will the volume of the balloon increase or decrease? Now, what we remember about Charles's Law is that it is inverse, or it's directly proportional, meaning that if temperature is increasing, then volume is also increasing, which is another way of saying that if temperature doubles, then volume is going to double with it. All right. So the first question is, will the volume of the balloon increase or decrease? It will increase, because that's as long as our temperature is increasing, and we're increasing from 22 degrees Celsius up to 31 degrees Celsius, and as a result of that, we know automatically that that's what's going to happen. Okay, sorry guys, I'm going to adjust my camera a little bit here. I'm going to try and turn off that autofocus because that's annoying. Did that help? Yeah, maybe it did. All right, we'll see. All right, so now what we have to do in B of this problem is we have to do a little bit of calculating. It says, what will the new balloon volume be? Well, let's go back into our problem up here at the top, and let's figure out what we know and don't know currently. So we know that 3 liters is a volume. We know that 22 degrees Celsius is a temperature. It's placed out on a hot summer day. We know we have a new temperature, but what we don't know is what will the new volume be. So if you remember, and I'm going to go ahead and point this out, that Charles' Law says that our initial volume over or divided by our initial temperature is equal to our new volume over our new temperature. And so if we're going to calculate that, we can calculate for these variables using these formulas over here, and I will kind of talk you through that here in just a minute, because I know that's a really busy document. So let's figure out what we have so far. What we have is we have V1 right here. We have T1 right here, and we have T2. What we don't have is our V2. That's what we're trying to find. Okay. Now, just a quick reminder, when it comes to Charles's Law, and you'll see this again when we do Gay-Lussac's Law as well, is that because we are dealing with absolute temperatures in these laws, that's the way that they were written, is we have to make sure that we convert everything to degrees Kelvin, because Kelvin is the temperature scale when we're dealing with absolute temperatures. Okay. So what I'm going to do over here on the side, I'm going to go ahead and I'm going to figure out my T1 and T2 in K, because right now they're both given in Celsius. So I'm going to go ahead and do my T1 right over here. I'll move this over a bit so you can see it. T1. And that's going to equal my degrees Celsius, which is 22 degrees Celsius plus 273. So my T1 is going to be equal to, I'm going to go ahead and do the math on that real quick. And that's going to be 295 K. So I'm just going to isolate that so I know where to find it. Now I'm going to do T2. So my T2, which is right here, which is 31 degrees Celsius, I'm going to go ahead and add 273 to that. So now my T2 equals 304. Okay. So now I have my T1 and my T2 converted to Kelvin. That's good. So now I just have to go ahead and set this up and solve for V2 because that's what I'm trying to find. So V2 is equal to what? So let's go ahead and come over to our little document that we have here. And if I'm looking at the Charles Law section of this document, and that's this little section right here, I'm going to look for my variable of V2. So I'm going to use this by simply coming over here, and the formula that I'm going to use is V1 times T2 over T1. So if I were going to write that on my paper, it would look like this. I'm going to go ahead and just put that right over here. So V2 is the same as saying V1 times T2 over T1. So that's what this means. What I've written right here is the same as what you see right there. Okay. So now what I have to do is I have to start plugging in some numbers. So my V2 is equal to my V1. So according to this problem, my V1 is 3.0 liters. Notice how I've put my units here. It's a big deal. Get those units into the problem. And I have to go to my T2. Now, again, you guys remember, we're using our converted numbers. So my converted T2 is going to be 304K. And over that is going to be, that's going to be over T1. And if you remember, we calculated our T1 to be 295K. So now what I'm going to do, because of order of operations, we always do our multiplication on top first. So I'm going to go ahead and crunch those numbers in. I've got 3.0 liters times 304K equals, now you guys, I'm going to take a second here, and I'm going to go ahead and cancel out the units that cancel out here. So I'm going to cancel out my Kelvin units, and what I'm left with is 912 liters over, because there's my liters unit right there, over my T1, which is 295. Now I don't have a unit on this because I went ahead and I already crossed my units out. So now down here at the bottom, V2, once I do my math here, 912 divided by 295 equals 3.09. And again, you guys, I'm dealing with my new volume, so I know my unit's going to be liters. And then I just circle that up, and there you go. So again, you guys, the big thing when it comes to your process in doing a Charles Law problem, the most important thing you can do first is to go through and read your problem and determine what you have. Determine what your first volume is, determine what your temperatures are. Once you've determined what your V1, V2, T1, T2 are, then it's important for you to go do your temperature conversions if you need to. Now, if you're given degrees Kelvin in the problem already, you don't have to do any conversions. But if you have degrees Celsius to start with, you must convert that to Kelvin before you go any farther in this problem. Okay? So let's look at, I'm going to go through the rest of these. I'm going to do this whole document, so just bear with me. It'll probably take me about 15 or 20 minutes. Now, of course, you don't have to watch the entire video. That's up to you. But if you want to, then just stay with me, okay? So we have this situation where our temperature is 0 degrees Celsius, and the temperature is changed so that the gas volume doubles. Now, I want you to remember the statement I made a couple minutes ago where I said that in Charles's law, if temperature increases, volume also increases. But I can also say that if temperature doubles, volume also doubles. Again, that's that directly proportional relationship. So if we go back to our problem here, it says the volume of our gas doubles. So this question, was the temperature increased or decreased? Well, if we doubled the volume, that means our volume increased. And according to Charles's law, when one increases, the other increases as well because it's directly proportional. So we know that this is also going to increase. Now, as far as what's the new temperature of the gas, we're assuming constant pressure because, again, that's one of the things Boyle's law tells us to do. But if we're doubling the volume, it also means we're doubling the temperature. So my first order of business is to convert this to Kelvin. So 0.0 degrees Celsius plus 273. So K equals 273. Now, if my gas volume doubles, it means I also have to double this temperature. So I'm going to take 273 times 2 because I'm doubling it. And once I do that, 273 times 2 is 546 K, because again we're using that unit. So that's what I'm going to write here, 546 K, because I've doubled the volume, therefore I've doubled the temperature. But again, I have to convert this temperature to degrees Kelvin. I did that. Now, if I want to convert this number back to degrees Celsius, I can do that too if I want. All I have to do is take this number minus 273, and when I'm done with that, 546 minus 273 is 273 degrees Kelvin. Wait, I got to make sure I did that right. 546 minus 273. Yeah, so that makes this 273 degrees Celsius if you wanted to go there. But again, you guys, because we're dealing with absolute temperatures, sticking with Kelvin is the way to go. All right, let's do question number 3. I'm going to move this over a little bit so you can more easily see that. It says the gas has a volume of 10.0 meters cubed at standard temperature, which is 273 degrees K, otherwise known as 0 degrees Celsius. What volume will the gas occupy? So we know we're looking for a volume here if the Kelvin temperature is doubled. All right, well, we know that our volume is 10.0 meters cubed, right? And we also know that if we double the volume or double the temperature, if we double the temperature, it means we're also going to double the volume. So all we have to do is take this times 2, and that's going to give us 20.0 meters cubed, which is what we are going to write here. Okay. Now what happens if the temperature is reduced to a fourth of its original value? And again, because temperature and volume are proportional, we can pretty much do the same thing. 10.0 meters cubed times 1/4. Another way of saying times 1/4 is saying 0.25. And then once we do that, we end up with 2.5 meters cubed. And again, we took this number because instead of doubling it this time, we took this volume and we reduced it in half, which means, or we reduced the temperature to this quarter, which means that we're going to end up with 2.5 meters cubed. All right, let's do number 4 down here. It says, suppose 500.0 milliliters of oxygen is collected at 298 K. Now, this looks good because notice, you guys, my temperatures are given to me in K for this problem, which means I'm not going to have to convert these to K. They're already listed in K. So let's take a look here. So we know this is a volume. This is a temperature. This is also a temperature. Suppose 500.0 milliliters of oxygen is collected at 298 K. What will the volume be if the temperature is increased to 323 K? While the pressure is kept constant. So what will the volume be if we change the temperature? Okay, so this, we automatically know that this is going to be temperature 2. This is going to be temperature 1. This new volume is going to be V2. And this original volume is going to be V1. So again, what we don't know is our V2. Now, because I don't have to convert temperatures, I don't have to worry about doing what I did up here and converting my temperatures. I can just get right into finding V2. So V2 equals, we're going to go back to our little sheet here. Again, we're in the Charles Law section, which is right here. We are looking for V2, which means I'm going to use this formula right here. And that formula is V1 times T2 over, that's what this little slash stands for, T1. Okay. Now that I have that, I can start plugging in my numbers. So V2 equals V1. Now, according to what I figured out earlier, V1 is 500 milliliters. Times T2, and if I'm looking, the temperature is increased right here to 323 K over T1, which we determined to be 298 K. And again, you guys, order of operations tells us that we're going to do our multiplication at the top first, so let's go ahead and do that. So we're going to take 500 times 323 equals 161,400 500. Now, as far as which units I'm going to be using here, so I need to make that look like a comma, is that I can cancel out my temperature units or my units Kelvin, which leaves me with 161,500 milliliters, and that's going to be over 298. So now it's just a matter of finishing this division. So V2 equals 161,500 milliliters divided by 298, which leaves me with 541.9 milliliters, because that's the unit that I have left, and that is a unit of volume. So there you go. Let's look at page 2, shall we? And I'm not going to do every problem on page 2. I'm not going to do the Boyle's Law problems for this particular activity, because you can just look at the Boyle's Law video and you should be good on those. So this is number 5. Now there's a lot going on in this one, so we have to make sure we pay close attention to what's happening in this particular problem. It says a gas occupies 560 centimeters cubed at a temperature of 120 degrees Celsius. In degrees Celsius, that's important, to what temperature must the gas be lowered if it is to occupy 400 centimeters cubed without a change in pressure? Now, like I said, there's a lot going on here, so let's take some time with this. I'm going to go ahead and get that out of my way to start with. If we think about what we have in front of us, well, let's just deal with what we know. A gas occupies 560 centimeters cubed. Well, centimeters cubed is a unit of volume, so I know that's going to be a volume at a temperature of 120 degrees Celsius. In degrees Celsius, what temperature must the gas be lowered if it is to occupy 400 centimeters cubed? So this ends up being, this first volume is going to be my V1. This 120 degrees is going to be my T1. And this volume is going to be my V2. What we don't know is what temperature. This is going to be my T2, so we don't know this one. Now there's a lot going on here, because if you're reading this question, you'll notice that it's telling you that it wants the answer in degrees Celsius. So a common mistake for students at this point is that because the answer is supposed to be in degrees Celsius, that you skip the conversion, because you're like, hey, it's already in degrees Celsius, I'm just going to go with that. But again, you guys, because Charles's law works in absolutes when it comes to temperature, this is what it means. It means that we have to convert T1 into Kelvin before we can solve for T2. Then after we get our answer, then once we get that T2, we have to convert it back to Celsius. So let me kind of show you what I'm talking about here. So what we're going to do to start with is we're going to take this T1 and we're going to convert it to Kelvin. So T1 equals 120 degrees Celsius plus 273. So my T1 is going to be equal to 120 plus 273, and that leaves me with 393K. And I'm going to go ahead and isolate that because that's just reminding me what I have. Okay. Now what we're going to do next is we're going to go ahead and figure out T2, because what we know, we figured out early on that we have our V1, we have our V2 right here, and we have our T1, but we don't have T2. So let's go here. T2 equals, and let's go to my little help tool here. Now the last couple of problems we were looking for V2. This time we're looking for T2, and we're going to use this little formula right here. This is V2 times T1 over, and again that little slash mark means over, V1. So let's write that out. Just going to put that right over there so you can see. Yeah, you still can't really see it. That's all right. So T2 equals V2 times, and I'm going to go ahead and see, V2 times T1. And again, you see that little slash mark right there, burp, burp, that little slash mark, over V1. And that little slash mark you see right here is the same as this underline right here. And again, you guys, that's going to be V2 T1 over V1. So now let's go ahead and plug in what we have. Our V2 we determined was 400 centimeters cubed. And we know that because this is the volume that we have after we change the temperature. That's why this is V2. And we're going to multiply that V2 times T1, which we converted right here to 393 K, over V1, which we determined to be 560 centimeters cubed. Now, one of the things I want to make sure that we know and understand is that we lowered the volume of this system. So we can already start to think ahead and say, all right, if we lowered the volume of the system, we can expect this T2 to be lower than our T1. So that's kind of how we're kind of check ourselves here. So let's go ahead and do some math here. And again, order of operations tells us that we should multiply these two top numbers first. Our V2 and our T1 should be multiplied together first. Then we'll divide by V1, which is that 560 centimeters cubed. So let's go ahead and do that. We're going to take 400 times 393, and that's going to give us 157,200. And as far as units, well, we're going to go ahead and cross those out. We're going to cross out our volume units, and this is going to leave us with K as our only unit over 560. So we'll come over here to our T2 then, and we're going to do some division here. 157,200 divided by 560 equals 280.7, and remember, this is a temperature, so I want my unit to be K. So we might think to ourselves, we are obviously done at this point because there's my temperature. But remember, you guys, what do we have to do? Our final answer needs to be in degrees Celsius. So now what we have to do is remember that if we are trying to go from Celsius to Kelvin, we add 273. Well, if we're going from Kelvin to Celsius, we do just the opposite. We're going to subtract 273. So my T2 in degrees Celsius is going to be 280.7 minus 273, and that's going to leave us with 7.7 degrees Celsius. So ultimately, that is my final answer for this particular problem. And again, you guys, one of the things that we have to remember is no matter what, we have to make sure that when we are going through the process of a Charles' Law problem, that we are converting our temperatures to Kelvin. Even if our final answer needs to be in Celsius, we have to convert it to Kelvin, get through our work first, get our answer, and then convert it back to Celsius. Okay, and that has to do with the nature of Charles' Law, which is dealing with those absolute movements of particles. Okay? So there you go. Now, like I said, I'm not going to do the Boyle's Law problems. You'll have some videos that you can watch that will go through Boyle's Law. And like I said, this is already a pretty lengthy video, so we will cut it short here. All right, you guys, have a great day. And if you have any questions, let me know.